Alright, so this is Griffiths Quantum Mechanics, problem 3.12. We're going to show that the expectation value of x is equal to this integral here. Okay, so these are the wave functions, except they're in momentum space, not position space. And then here is just an operator on the inside. And so essentially what we're showing here is that when you're going to be working in position space, so let me write this out. So position space this, alright, x is just x when you put it in. That's why we're in position space. Alright, and momentum, though, we have this operator where it's, the minus IH bar, or the h bar over I, and then the derivative with respect to x, okay? In momentum space, I should have just written p space, right? But momentum is just momentum, okay? But when we want to use an x in momentum space, now the x is an operator, okay? H bar over I, d by dp, except there's a minus sign right here, okay? So that's the difference. And you can use either one. Usually position space is more helpful. But so this operator right here is just this, right? So all we're saying is this is the same as, if we were writing this in position space, but the way we would write it is just, we'd use our position space wave vectors, right? Psi, right? And then I started writing an operator, but it's not. It's just x. And we're integrating with respect to x, all right? So basically all we're saying is you can do this in either space. Either space is fine, but just in momentum space, you have to remember the minus sign here on this operator. Otherwise, you can just take x and p and basically switch them up. Okay. All right. So we're going to show this this right here. It's going to be a little bit tricky. Okay. So let's see what we've got. Let's start by writing it out in position space, right? Okay, so use our position space, and then we have an x, and then our other position space, right? So this is identical to this equation that we already wrote. I'm going to put a parentheses around this just so maybe it looks more like an x instead of multiplication or something weird. Okay, so now what we're going to do is we're going to write these position space wave functions in terms of the momentum ones. All right, and the momentum one is just the Fourier transform of the position one, and the position one is just the inverse Fourier transform of the momentum one. So so we'll be having here for this one, we have the inverse Fourier transform. Okay. And all these integrals are minus infinity to infinity, right? Okay, so now and this is a little weird because we're taking the complex conjugate. So it's not going to look like a Fourier transform or an inverse Fourier. It'll look like a Fourier transform with a minus sign right here. IPX over h bar. Okay? And this is integrated with respect to momentum. All right? So this one looks a little weird because of the star. But okay? And then to save space, let's go ahead and write the little, no, let's not do it yet. Okay, so I still have my x here, and then I'm going to write this x, the position space wave function right here as the inverse Fourier transform of the momentum space wave function. All right, so again, we have our 2 pi h bar, 1 over square root of 2 pi h bar out front. We have our integral. This time there's no star, right? Okay, and then it's e to the plus I px over h bar. Okay, and this is integrated with respect to position. And then this integral way out here that we probably forgot about by now, that is with respect to position. I think I said position. This is momentum. I may have slipped up there when I spoke. Okay. All right. So one thing is, well, let's bring a, should we bring the constants out front? Why not? Okay, so here's a constant and here's a constant. We'll bring those out front. Now we have our integral with respect to x. We'll see if we can smash all this in the middle here. All right. This integral here, real quick. Okay, so now since this little integration right here is with respect to momentum, it sees this x as a constant. So we can bring this x into this integral, all right? And once we do that, we're going to have this quantity. I don't know if I can write it up here, but I'll try. Right, we have this little hint equation, right, that he gives us. So x multiplied by e to the I px over h bar, okay, is equal to minus I h bar d by dp e to the I px over h bar. Okay, so basically so once we pull this x into this integral, we can see this guy right here. So once we pull the x in, we'll have this side, and we're just going to swap that for this other side. All right, so okay, we already brought our constant out. We're going to have a minus sign, and I'm going to just bring out a minus I h bar, just because. All right, so we won't have this x, and we are going to end up with this phi. Okay, I should make them all capital like I did before. Okay, I brought this minus I h bar. All right, I'm just kind of stumbling around here. Okay, I think I've written it all. Okay, I think I've got this. So I need my other parentheses or bracket. Here we go. Okay, I think we're good. All right, so now what we're going to do, since these wave functions all go to 0 at infinity, right? They're all normalizable. We can do our little trick where we switch the derivative from this part over to the other part. Integration by parts, right? And so we just do that, but we also get a minus sign out of it. Okay. So oops, that's a B. All right, so here we go. So now we're going to kind of bring all these integrals together. Okay, and what we can do is, the way we're going to do this is, we have to keep the variables of integration distinct, okay? So I'm going to change one of these p's to a q so we know which integral they belong to, all right? It's going to get a little bit tricky here, okay? All right, so we're bringing all of our integration signs. I'm going to go ahead and bring this IH bar out to the front as well. We're bringing all of our integration signs out to the front, and you can't like do this with the same variable of integration here. All right, so I'm going to go ahead and change this first one here to a q. All right. So here on the end we'll have dq, dp, dx. Okay. So I'm going to have e to the I. I'm going to combine these two exponential terms. All right, this one, the p is positive and q is negative. All right, the p minus q, like this, x over h bar. Okay, and then what we have, all that we have left over is this, except I'm going to make this more explicit. I'm going to put this as a function of q now, right? Okay, and then we have d by dp, and this one is a function of p. Okay, all right, so normally you can't just like shift all the, you know, when you're multiplying two integrals together, it's not just the integral of the multiplication, you know, when you're using the same variable. But since we used a different variable name, right, we're just making sure that we don't get confused and call these the same thing. Okay. So the only thing that depends on x still is this term right here. All right. Now here's the weird part. Way back when, we had this really strange formula. Where did it go? In one of our old problems. I should have written this beforehand. So this is from problem 2.26, okay? We found this really weird formula that 1 over 2 pi integrated minus infinity to infinity, right, of e to the I k x with respect to k is equal to the delta function of x. Okay? So I'm going to rewrite this as 1 over 2 pi, this integral, all right? And it's kind of confusing because k is x. Well, or x over h bar rather, I suppose. All right, so we are going to have a dx over h bar over here. Did I do that right? Just double check. No, what I'm gonna just do is call x over h bar a different variable, so z or something. Okay. So z equals x over h bar, like that. So h bar dz is equal to dx. All right, so we still do have this division by h bar. I'll just put it out here. Okay. Or is it multiplication by h bar? I'm so bad at my calculus. Okay. I think that's right. Is that right? I think that's right. Okay, so we have a multiplication by h bar. All right, here we go. Okay, and then again, the way, again, this is kind of confusing because x is actually p minus q and k is x, or in this case z. All right, a little bit messed up there, but okay, I'm just gonna double check this, make sure this is okay so far. All right, I think we're okay, I think. All right, let's go ahead and put this in. So, so this takes care of our x integration, right? And when we put this in, we're going to get rid of, we'll get rid of this h bar and 2 pi down here, okay? So what we're going to have is an IH bar, right? And then we'll have our our Q and P. But now we have this P minus Q delta function. Okay. And then we have our Q and P wave functions. All right. So basically this delta function just sets P equal to Q. And we are h bar. Okay, so now let's go back to p. And it also gets rid of one of these integrals, right? This one's a conjugate. Okay, so if we look back at what we were trying to show in the beginning, we've just done it. All right, because we could just divide this I down. So let me just write this into the original form, just to. All right, so I'm going to have this h bar, and when we move the I to the bottom, we get this minus sign. Okay, all right, so now we have this term right here that we were looking for. All right, so there we go. That's what we set out to prove. So again, it just comes back down to whether we're in position space or momentum space. So this is just the x, the operator for x, this minus h bar over I d by dp. And so we're still just taking an expectation value of x, except in the momentum space. So if we were to take the expectation value of momentum in this space, it would look just like this. Except we don't need an operator for momentum in the momentum space, we just put in momentum. So anyway, just kind of to show how this generally works.